So this is the equilibrium lab. In this lab, you examine the reaction between potassium thiocyanate, that's KSCN, and ferric nitrate, or iron 3 nitrate, FeNO3. And so the first part of this lab is actually determining whether indeed this lab reaches an equilibrium or whether it goes to completion. So far in the course, we've really only talked about reactions that go to completion in Chem 103. It's all about reactions that go all the way. But in fact, many reactions actually reach some sort of balance point where the rate of going forward and back actually equalizes, and we call that point the equilibrium point.
So this is part A of the equilibrium lab. In part A of this lab, so we set up to figure out whether this reaction goes to completion or whether it ends up in a state of equilibrium. So what I've done here is I just want to show you the reactants that we're using here. Okay, we have the same concentration, 0.00200 molar of potassium thiocyanate on the left, that's KSCN, and FeNO3 on the right. And what I've done is I've measured actually 3 milliliters of each of those into each of these two 10 milliliter graduated cylinders. The direction was called for 2, but I always like to make a little bit more in case I spill some on the bench. Okay, so now what I'm going to show you is what it looks like as I mix these two things together. Okay, so I have my 2 graduated cylinders. One has the ferric nitrate, one has the potassium thiocyanate. I'm going to mix them together, and you can see what immediately happens is I get a very beautiful amber colored liquid. Okay, that the color is the product. We call it the complex. Okay, and what I'm going to do is divide that up into these 4 test tubes. So some in the first, in the second, the third, and in the fourth. I'm going to be taking and testing each of these small samples by adding different things to it. So to number 1, I'll add distilled water. Number 2, I'll add a couple of crystals of the ferric nitrate. To number 3, I'll add the potassium thiocyanate. And to number 4, we'll add potassium nitrate. This is going to allow us to figure out which of those ions, right? Because there's 4 ions in solution, 2 positive ions and 2 negative ions. And we're going to figure out which of them are actually involved in the reaction. And we're also going to figure out whether this reaction goes to completion or exists at a state of equilibrium. Okay, so I've got my 4 test tubes. Okay, each with a little bit of that solution, 1, 2, 3, 4. This is the solution that results when you mix the ferric nitrate and the potassium thiocyanate, equal amounts of 0.002 molar of each. Okay, and I'm going to do a few tests on this to see what happens when I add various things. So here I have one of the samples, and I'm simply going to add a little bit of distilled water, just as a control. And basically, nothing happens, as you might expect. I mean, maybe it's ever so slightly lighter, but I don't even think it is that. And now I have another sample. I didn't exactly put equal amounts in these, but it just doesn't matter. I'm going to add to this a couple of crystals. And what do you see happen to the color? So if you compare that to the color here, okay, you can see that this is the one where the ferric nitrate was added. This is the one with the distilled water. It was basically the same as the original. And you could see that the color deepened. Okay, if you want to, that's the second one. Okay, and now for number 3, I'm going to add a few crystals of the potassium thiocyanate. That's this other one. So let me do that to open the thing. Wash off my spatula. Okay. Here I have the test tube that I'm gonna, oh, that's not the one. This is the one I'm gonna add it to, number 3. Okay, I'm gonna get a crystal here, or a few crystals. These are very hygroscopic. They absorb a lot of water, so I'm gonna be, there, look at that. That was pretty dramatic. Okay, so the color definitely deepened. Okay, and now the 4th one, I'm simply going to add a crystal of, or a few crystals of potassium nitrate. That's over here. Get the potassium nitrate. Oops. It's very slippery. I'll get a bunch. Here's my test tube. Potassium nitrate. Really, nothing happens. Okay. If you compare that to the distilled water one, it's basically the same. Okay. If anything, it might have gotten a little lighter. It's kind of weird. All right, so I have my 4 test tubes. Okay, so the first one just had distilled water added, just a tiny bit. Color basically didn't change. The second one, it's definitely deeper color when you add that crystal of, I believe it was a ferric nitrate. Here, it deepened a lot when you added the thiocyanate. It may have added more, actually, than the other one. And here is when you add potassium nitrate. Basically, nothing happened when I did that. Okay? So there's my 4 test samples. Some of them are hiding behind things. Okay? 1, 2, 3, and 4. All right. So now what does that mean?
Hi. So in the next part of this lab, that's part B, we pretty much have already determined that the reaction comes to an equilibrium. That's what the part A, I'm sure that you discussed this in your lab, well, on Zoom or Blackboard or whatever, and came to the conclusion that the reaction had to have come to an equilibrium. But what we don't know, and we actually know which of the chemicals are involved, right? We know it's the iron and the thiocyanate, but we don't know the proportion that they react in. Is it 1:1? Is it 2:1? Is it 1:2? So that's what this part is all about. So in this part, what we're going to do is we're going to make up 9 different samples of our reaction mixture. Okay, so here I have 9 test tubes. Okay, and into these test tubes, so in the first test tube, you can see from the list here that I'm going to add a certain amount of milliliters of the FeNO3 and the potassium thiocyanate. So in solution 1, it's 1 of the iron compound and 9 of the potassium thiocyanate. In number 2, it's 2 and 8, and then 3 and 7, etc. So we're basically making up 9 solutions with consecutively increasing amounts of the iron nitrate and consecutively decreasing amounts of the potassium thiocyanate. And then what we're going to do is measure the absorbance of each one of these samples and figure out from the absorbance, because the absorbance is proportional to the amount of complex, right? Because it's the complex that's colored, and that's the thing we're going to measure the absorbance of. So we'll see what happens to the concentration of complex for all these different mixtures, and it will allow us to figure out what the stoichiometry of this reaction is. Okay, so what I'm going to do, it says to use a burette, but I'm more comfortable with a pipette. And it also requires less glassware to be washed. So here's my 9 test tubes. Okay, so I can actually get that focused
almost on there. There we go. So what I'm going to do is I'm going to take my 10 milliliter graduated pipette, okay, and I'm going to use it to pipette 1 milliliter of the ferric nitrate into test tube number 1, and then 2 into number 2, and then 3 into number 3, etc. Okay, that's what my plan is anyway. So I have, here's a pipette for the ferric nitrate, and my pipette bulb down here. So I'm just going to go down one big mark. One in there. Two in the next one. Three in the next one. I don't have enough for 4, so I'm going to fill it up again. So into number 4, I'm going to put 4 milliliters. I'm going to get 5. I'm going to have to do more and more pipetting. 6. I put 6. 1, 2, 3, 4, 5, 6. I'm just going to put 7. 2, 3, 4, 5, 6, 7. Good. 8. That's a little drippy. 5, 6, 7, 8. And finally 9 and the last one. Oops, drippy pipette. Notice I'm not taking the blame for that. I'm going to blame it on the pipette. Eight, 9. Okay, good. All right, I'm going to do the same thing in the opposite order for the potassium thiocyanate. Okay. So here I have the potassium thiocyanate. honestly don't know if this is even visible. So I'm going to start with 9. I'm going to put 1 in 9. And I'm going to put 2 in 8, etc. Zero. 1 in here. 1. Notice I'm forming complex. 1, 2. 1, 2, 3. 4 on this one. 1, 2, 3, 4. I get some more. My arm needs a rest. And you can see already that. So this was the first one. It's pretty light. I have to mix it up. The second one you can't see because it's behind there, but they're getting successively darker. It's an important observation. Now I've got to put 5 milliliters in the next solution, which is solution 5. Just check to make sure that's correct, and it is. So I'll put a tricky pipette. 5 in here. Milliliters. You can see the color, nice and dark. Here I'm going to put 6. I'm just going to add a little bit more to get to the okay. 6. 1, 2, 3, 4, 5, 6. Some more. So for 7, I'll go from the 1 milliliter to the 8 millimeter mark. 6, 7. I'm going to get 8. I guess it would be a lot of pipetting if students were doing this. That's why we use the burette when students do it. 8. 1, 2, 3, 4, 5, 6, 7, 8. And finally, the last one, thank goodness. Starting at 0, go down to 9. 4, 5, 6, 7, 8, 9. Good. Whew, done. Okay. So just to see what everything looks like, first of all, I'm going to mix everything. This was the solution 9, very light. 8, it's pretty light too. 7, 6, 5, 4, 3, 2, and 1. Now I'm going to take and put 10 test tubes, smaller ones, in front of those others. Steal them from the other experiment. 1, 2, it. Is that better? Six, 7, 8, 9. I'm just going to transfer from the big test tube to the little test tube. That's the easiest way to do that. Try to pour it without spilling it. Okay, that's solution 1. Solution 2. This is not so hard. Solution 3. I'm filling them too high, but that's all right. Solution 4. Oops, that was fast. 7, 8, 9. All right, so here's my 9 samples. Okay, a nice test tube rack, all nicely labeled. And now I have to get the little instrument here, the little, well, we used to call them Spec 20s, but it's not even made by Spec anymore. They're made by Flynn, okay? So I have to get my spectrophotometer ready. So here is the little spectrophotometer we call the Flynn spectrophotometer, made by the company Flynn. And what I'm going to do is set the wavelength to 540 nanometers. Let me take the sample of water. So this is a sample of just plain old water. Put it in here. And I see, I want to zero that. So I'm going to hit the auto zero here. It's blanking that sample out. So I'm going to get my sample 1. .164. Number 2, you should be writing this on your data sheet. 0.261. Number 3, 0.350. All right, next is solution 4. 0.370. And then solution 5. 0.404. And number 6 is next. 0.394. I'm going to blank this again. And then I'll do solution 7. Okay, I've got solution 7 now. .334. Solution 8. It's getting lighter. Number should be lower. 0.257. And then finally, let me get rid of 8. And then solution 9. .131. Okay. So these are the 2 solutions that must be prepared for part C. Each will have 10 milliliters of the potassium thiocyanate, KSEN, of 0.00200 molar. Here's the other solution I'm going to make. Okay, this is called one of them is called the standard, one of them is called the unknown. Okay, in the standard, you'll notice there's a much higher concentration of the other reactant, the iron nitrate. It's 10 milliliters of 0.1 molar, as opposed to here, it's almost rubbed out, but it's 10.0 milliliters of 0.004 molar. So in the standard solution, we're adding a whole lot more iron nitrate. And as you know, when you add a lot of one reactant, it drives the reaction to the right, okay, by Le Chatelier's principle. So it's as if the system at equilibrium were responding to adding a large amount of the ferric nitrate. And so this reaction will basically very nearly go to completion. And that's how we will be able to figure out what the concentration is of the complex. That's the brown, amber-colored complex that forms. And that's why we call this the standard, because we will be able to figure out the concentration of this solution. So what I've already done is I've taken and I've pipetted with this 10 milliliter pipette here. I've pipetted the same 10 milliliters, well, not the same, but 10 milliliters each of the potassium thiocyanate into each of these two flasks. And now I'm going to pipette 10 milliliters of the 0.1 molar into this marked B, but it's the standard. I'm going to put it into this solution, and then I'm going to put 10 milliliters of this 0.004 molar ferric nitrate into this solution. And hopefully I can capture this on the camera. If I can't, I apologize. Okay, so let me take and put 10 milliliters of this, and of course it's going to turn brown or amber, whatever you call that nice color that the complex forms. So 10 milliliters, look at that, if you can see it, which I hope you can. Okay, and now 10 milliliters of this one. Hold it at eye level. Good, right on the 10. All right, now let's take a look at these two solutions, all right? So the one on the left, which I'm calling the standard here, is extremely dark. I've driven that reaction all the way to the right. There's a lot of complex in there. But this one is much lighter. This is what I call the unknown, okay? So what we're going to do is we're going to figure out, we're going to calculate what the concentration is of the standard. Then we're going to use the difference in the absorbances of these two samples to figure out what the concentration is of the unknown. And once we know that, we will be able to figure out what the equilibrium constant is. We will have to solve an ice problem. Okay, all right, let's go and do the absorbance measurements next. Okay, so now I'm going to measure the visible absorbance of these two samples. I'm going to change the wavelength slightly. I'm supposed to run this at 560 instead of whatever it was before, 540. It's basically the same peak, but I want to get absorbance readings that are in a range that makes them more accurate. So if I stayed at 540, they would be too high. And this instrument doesn't measure very high absorbance as well. All right, so I'm going to put in my water blank, and I'm going to zero it. Oops, I have a leftover test tube in here. Oh well, put that aside. Put in the water. And And I'm going to zero it. Okay, blanked, zeroed. I'm going to first put the standard. This is the absorbance of the standard. If I had left it at 540, this would probably be like 2 absorbance units, or 1.8, and that's really too high for this instrument to measure. So I turned it, the wavelength, I changed the wavelength a little. 1.088. That's the absorbance of the standard. And now, 0.328 is the absorbance of the sample. Of the unknown, I should say. Okay? So with that, you should be able to do the write-up, do all the calculations, and finish up this lab. And all I have to do is clean up. Bye-bye.